forms and binary geometries from generalized Permutahedra. Boy, that's a. I bet if you try to repeat that 10 times, you won't. It'll be a big tongue twister. Yeah.
Yeah. Thank you. So, yeah, it's a longish title with fancy words, but hopefully it'll be clear by the end of the talk. So this talk is based on this particular work, which I did with Song He and a couple of his students from China. So the talk has a bit of technical details, so feel free to stop me anytime in between. And I try to go slow. Okay, so scattering amplitudes are at the heart of high energy physics. The usual method for computing scattering amplitudes using a Lagrangian and evaluating Feynman diagrams uses a nice physical picture and makes locality manifest. But it's been known for some time now that this method is neither very efficient to compute scattering amplitudes, nor is it particularly useful for revealing hidden symmetries of structures. So it's not particularly efficient because the number of Feynman diagrams, as we know, grows quite rapidly with the number of external particles. But the scattering amplitude obtained by summing over all these guys is, can be something very simple due to various seemingly miraculous cancellations. And it's not very useful for revealing hidden symmetries, like the dual conformal invariance of n equals for super Young Mills or the BCJ double copy relations, which relate Young Mills and gravity amplitudes. So to overcome these things over the years, several on-shell methods have been developed, like unitary cuts, BCFW recursion relations, CHY, etc., which sort of bypass the use of a Lagrangian and together have been called the amplitudes program. But it's not fully clear how these various methods, these different methods, are manifestly related to each other, even though they all compute the same object, which is a scattering amplitude. So you can say one of the main goals of the amplitudes program is to sort of fit all these different looking methods into some sort of unified framework. So candidate framework for thinking about a class of scattering amplitude has been developed over the past decade or so and is called the positive geometry program. So some key features of this framework are that scattering amplitudes are to be thought of as differential forms living in kinematic space as opposed to functions living in kinematic space. The framework is independent of spacetime, and unitarity and locality sort of emerge as consequences rather than being inputs. So for example, unitarity is encoded by factorization. It sort of follows from the geometry itself. By factorization of the geometry, I mean the geometry locally looks like products of geometries of the same type. And locality is encoded by the physical poles being located on the boundaries of the geometry, nowhere else. So what is the positive geometry? So positive geometry is a closed geometry with boundaries of all codimensions. For example, a circle is not a positive geometry because it has no zero-dimensional boundaries, but a square and a triangle are positive geometries. Polytopes are sort of the simplest examples of positive geometry. Positive geometry has a unique differential form, which is called its canonical form. And the canonical form has the following properties. So it has simple poles on the boundary and nowhere else. At every boundary, if I compute the residue of the form, then I get the canonical form corresponding to the boundary. And if the geometry is just a point, then the canonical form is plus minus 1. If I have a pair of positive geometries, then the canonical form of the product is the wedge of the individual canonical forms. And finally, if I have a map from one positive geometry A to another positive geometry B, then I can get the canonical form of B by pushing forward the canonical form.
Prashanth, sorry, I got disconnected because of bad internet connection. So can you just tell me briefly the motivation behind considering positive geometry? Is that a conjecture or is there something more to it?
So over the past 10 years or so, people have been finding these surprising connections between some sorts of geometric objects and scattering amplitudes in certain theories. Okay, so the beginning of the whole thing was the Amplituhedron itself for planar n equals 4 superangles, which was something very mysterious at the time. And then subsequently, this was sort of extended to some scalar theories also, like bi-adjoint phi-cube theory, which is part of what we're going to talk about today.
Yes.
So since the connections kept getting stronger and stronger, people sort of introduced some background. They thought maybe we should introduce a framework through which all these things can be better said.
Okay, and just to understand the philosophy a little bit more, so you're saying that the usual things that we use associate in quantum field theory, like locality and unitarity, those are going to be replaced by something geometric, like okay.
So fundamentally, the theory is defined by the positive geometry. So you just have the positive geometry. The amplitudes emerge from the canonical form. I'll tell you details after some time. And everything, I mean, unitarity and locality and all things we usually associate in quantum field theories follow from properties of the geometry. So everything is geometric.
Okay. And you're going to define positive geometry more, or is that all that you're going to say on this slide?
No, that's all I'm going to say for now. It can be made very precise and so on by introducing more definitions, but I will not do that. I will only, for now, for us, this much is enough.
Okay, and just to clarify, the notion of positive geometry, that is not a basis dependent notion. Like, I mean, what I mean by that is that what you're calling positive geometry, is it going to, is the definition or the criteria that you're using to define a positive geometry going to change if you changed your basis vectors?
No. It's not something which depends on the basis vectors.
Okay.
Yeah.
Okay.
Okay, so I haven't been very precise with the definition, but it doesn't depend on any of those things.
Okay.
Okay, so 0 and 1-dimensional positive geometries are just points and lines. We can construct the canonical form for any positive geometry by starting with a simple ansatz, that is with saying that the form has simple poles on all the boundaries, and then by repeatedly taking residues and demanding that the residues are plus minus 1. So let's look at an example. So let's consider a line segment x between A and B. So so the ansatz is, it has poles. It should have poles when x is A and x is B, and I can put a constant alpha. The one form, so it's dx. Now I can take residues. Right? I go to the pole at x equals A and the pole at x equals B, and demand that those things have to be plus minus 1, because the canonical form for a point has to be plus minus 1. So this tells us that alpha should be either A minus B or B minus A, and you can choose either. I choose A minus B, and we get the canonical form to be this, like 1 by x minus A minus 1 by x minus B dx. So once we factor out the top form from the canonical form, we get a function for the canonical function. And as we'll see, this canonical function is what is actually related to the scattering amplitude. Okay, so having defined these things, let me summarize what the framework is. Okay, so in the positive geometry framework, for a given theory, there is some putative positive geometry living in kinematic space, and then the canonical form of this positive geometry is pulled back. It gives you the scattering amplitude. So that is the framework. So this has been sort of established for all loop ABHY amplitudes in planar n equals 4 superangles, with the positive geometry being something called the Amplituhedron, and for tree level and one loop amplitudes in bi-adjoint phi-cube theory, where the positive geometries are called generalized associahedron. Okay, so here is an outline of my talk. So in the first part, the talk essentially has 3 parts. In the first part, we are going to review this connection for bi-adjoint phi cube theory and the associated positive geometry, which is called the ABHY associahedron. In the second part, we are going to sort of generalize this notion of canonical form to general polytopes and study their properties. And we'll see that this naturally leads us to some string amplitudes. In the third part of the talk, I'm going to define what are called binary geometries and so these are objects which sort of have nice properties, including factorization at finite alpha prime. Okay, so let me start with the first part, positive geometries in canonical forms. Okay, so I'm going to review the story for bi-adjoint phi cube theory. So some notation first. So the kinematic space Kn of n massless momenta is a space which is spanned by the linearly independent Mandelstam variables subjected to momentum conservation. So the dimension of this space is n choose 2 minus n. The n condition is due to momentum conservation, and so the dimension is n into n minus 3 by 2. More generally, for any set of particle labels, I can define the generalized Mandelstam variable Si, which can be written as a sum over the usual Mandelstam variable. Okay, so the bi-adjoint phi cube theory is a scalar field theory of field transforming in the adjoint representation of 2 gauge groups. And it has the following Lagrangian. The tree-level amplitudes in this theory can be decomposed into some group theoretic factors and what is called a double-colored amplitude, Mn sigma sigma tilde p. So we consider what are called planar amplitudes in this theory, which corresponds to sigma and sigma tilde being 1 to n, which is called the canonical ordering. And we shall sort of restrict to this ordering for simplicity, and we will omit sigma, sigma delta, etc. for the rest of the talk. Okay, so another useful basis for kinematic space, apart from the Mandelstams we discussed, are given by the so-called planar variables Xij, which are defined in terms of these generalized Mandelstam variables that I defined a few minutes ago. So it's straightforward to see that xi I plus 1 vanishes because of masslessness, and x1n vanishes because of momentum conservation. So again, you have n choose 2 minus n relations. It's n into n minus 3 by 2. In fact, these two things can be translated to each other by a simple linear relation, which I have defined here. Sij is xij plus 1, xi plus 1 j minus xij minus xi plus 1 j plus 1. Okay. So now let's consider a toy example and try to see how all the features of the positive geometry framework that I talked about.
So xi's are independent, huh? I mean completely independent. There's no relation between xij's.
Yeah, once you so basically there are two relations, right, where they go to 0, which is just masslessness and momentum conservation. Apart from that, they are all independent.
Oh no, but I was wondering that Si's J's are the Mandelstam variables and they have relations. But if you write it in this fashion, this xi j is equal to x, these x's are totally independent, or?
You mean amongst themselves?
Yeah, yeah.
So if you omit the last label, so there are some relations, but if you omit, if you restrict I and j to less than n, right?
Yes.
Then you can see that they are all independent.
Okay. So, but if you write Sij's like this, automatically Sij's satisfy momentum conservation.
Yes.
Right? I mean, yeah. Okay. Okay. Yeah. Go ahead.
Okay. Yeah. So now let's look at a toy example and see how all the features of the framework I mentioned are enforced or how they come about. So let's take n equals 4 3-level amplitude. It's a planar amplitude. So 1 over s plus 1 over t. So the question we want to ask is how can we get this from a positive geometry? So one straightforward candidate for a positive geometry comes from the kinematic relation s plus t plus u is 0, which is a straight line. Now, like I said, the geometry must have boundaries corresponding to poles of the amplitude or locality. So it's natural to impose these positivity conditions, where s is positive and t is positive. Now we also need to impose an additional constraint to identify a one-dimensional subspace in kinematic space, and that is done by choosing u to be a negative constant. So the positive geometry becomes s plus t equals c, which is just a straight line. Now the second feature of the framework was to treat amplitudes as differential forms and not functions living in kinematic space. So this we do by promoting each propagator to d log of the propagator. So 1 over s sort of goes to d log of s or ds over s. And similarly for t. Now I have various possible choices of sign that I can put. I can put plus minus for each of these terms and add them up. But for the moment, just let me just choose this sign where I have ds over s minus dt over t. So if you take this one form and you pull it back onto the subspace, s plus t is constant. This gives you the right scattering amplitude once you factor out the top. Okay, so now about the issue of the sign that we ignored. So the relative minus sign was really important to get the right amplitude. It also made sure that the differential form was well defined not just on kinematic space, SNT, but also on the projectivized version of the space. So the one form I wrote is basically d log of s over t. And so this form is invariant when I scale SNT by any arbitrary function of SNT. So the form remains the same. And this is called projectivity. And we'll see that this projectivity is what helps us fix a unique scattering form.
So is there something restrictive about the fact that you just had two channel symmetry? So what about an amplitude which is 1 over s plus 1 over t plus 1 over u? Would that also have a similar canonical form?
It won't. So basically, there's an inherent problem there, right? Because you'd still get one forms there. So first of all, we are talking only about planar things. So there's no 1 over u. If you were to consider such things, which actually happens for pi-4 theory.
Yes.
Right? So there you can see that there's an inherent problem right from the start, because your positive geometry should be something which is one-dimensional, which has to be a straight line, but you have three boundaries.
Yes.
So it doesn't make sense. So what actually happens is that for such cases, you don't have a single positive geometry which includes the whole thing. You have a class of positive geometries for different combinations of these variables, and then you have to do a weighted sum over the canonical forms.
I see. So the point is that so suppose I have identical particle scattering, which would have three channel symmetry. So those kind of things you would require this weighted sum to describe.
Yes.
I see. So basically, is it the
the positive geometry? So we are all the positive geometries of the polytopes that we are considering are what are called simple polytopes. That is each vertex, if it's a d-dimensional polytope, each vertex has exactly d facets touching. For these guys, the differential form is easy to write down. The canonical form is sort of easy to write down. Okay. Right. So another possibility is that you have some non-simple geometry which gives you these things. It's not been explored, but it's a possibility. We don't even know how to write down the differential forms corresponding to those guys and so on.
I see. And the fact that you're considering simple poles, that's an assumption. I would have thought that the fact that a scattering amplitude only has simple poles will come out as a consequence of factorization or something like that. I mean, something more profound than just putting it in an assumption.
Yeah.
So yeah, tell me.
Yeah, as of now, this is a toy example, right? We're just trying to tell you, I mean, and how the ideas are enforced.
Okay.
So it's something. How do you get a geometric object? As of now, there's no well-defined method as such. But once you know what the positive geometry is, everything emerges from there.
I see.
As of now, we are working backwards.
Okay. Yeah.
Yeah. To be pedagogical. Yeah. Okay. So this requirement of projectivity helps us fix a unique scattering. That's the claim. Let's see how that comes about. So we can generalize whatever to n+3 particles, because the n+3 particles have n propagators, like your graphs have n propagators. So you can write down a differential form for each such graph by promoting the propagators to d log of propagators and taking a wedge product. Now you can assign a sign ±1 to each of these guys, and then you can such that it's consistent with all the flipping in the wedge product, and you can add them all up. So this form is what is called a planar scattering form. Now there are many possible planar scattering forms. There are 2 to the G planar scattering forms, if you like. So each sign of G can be ±1. Now projectivity is what helps you get a unique planar scattering form up to an overall sign. So let's see how that comes. So consider 2 planar graphs G and G prime, which are related by a mutation. That is, one can be obtained from the other by the exchange of a channel in a 4-point subgraph. Let xij and xi I prime j prime be the mutated propagators, and let xib jv denote the rest of the propagators. Then if we scale the mutated propagators by some function lambda, it could be a constant, it could be a function of the rest of the variables, doesn't matter. Then the dependence of lambda on the scattering form is just the following. So I have sine of g plus sine of g prime, d log of lambda, with some other. Now, projectivity tells me that there should be no dependence. So this has to go to 0. And this is what gives us the sign flip rule. It says that 2 graphs are related by a mutation if they have opposite signs. 2 graphs related by a mutation have opposite signs. So this sort of helps me fix a unique planar scattering form up to an overall sign. Okay. Now let's define a few other things. So the planar variables xij are sort of dual to the diagonals of an n+3 gon, where the edges of the polygon are just the momenta. And in fact, planar cubic graphs with n edges are in a 1-to-1 correspondence with triangulations of n-gons, and the correspondence is visual. Simply how to translate from the graph to the triangulation and vice versa. So we would like to identify a positive geometry onto which we can pull back the planar scattering form to get the cubic amplitudes. That is the goal. And as we did in the toy example, we can impose a positivity constraint and say that all the xij's are positive. Now, since our planar scattering form is n-dimensional, we need to impose n into n minus 3 by n into n minus 3 by 2 minus n constraints, right, to get an n-dimensional object. And these constraints are just given by setting all the Mandelstam variables Sij to negative constants whenever I and j are differ from each other by more than 2. And the reason why this is justified is that you can see that none of these Mandelstam variables ever appear as any physical poles for any planar amplitude. So we just like u was just like u in the toy example. And we get a polytope by taking the intersection of these two spaces and giving a set of inequalities which will carve out polytope. claim is that these constraints always give you an n-dimensional convex polytope. For example, in the 5-particle case, we have these constraints. S13 is minus C13, S14 is minus C14, and S24 is minus C24. We can translate from the SIJs to the XIJs by that relation. And we can solve those relations in terms of some basis, say X13, X14, and get the other three guys, X35, X25, and X24. Now, after I do this, I impose positivity of everything, right? So X35 is positive, X25 is positive, and X24 is positive. You can see that these set of inequalities give you this region, which I've shown in red, which is a pentagon in the X13, X14 space. Okay. Now the claim is that this convex polytope we always get is a very special polytope, which is called the associahedron, and the canonical form of the associahedron is the planar scattering form pulled back onto it. So let me tell you what the associahedron is before that. Okay, so the associahedron is a combinatorial polytope which has been sort of well studied, and it's naturally associated to triangulations of convex polytopes with n diagonals. There's an iterative definition where you start with any triangulation of an n-gon and you start flipping the diagonals. So what you do is in the first step you can choose any of the n diagonals and you can do a flip. By flip I mean it's a triangulation, right? So each diagonal is contained in some unique quadrilateral. So by a flip I mean going to that quadrilateral and replacing the diagonal by the other diagonal. For example, in the picture here, there for the line, the triangulation is just dividing the square into two triangles, and the flip would have been to replace that diagonal by the other diagonal. So you repeat this process till none of your original diagonals are left, and you get a convex polytope. You get what is more precisely called one graph of one skeleton of a convex polytope, which is called the associahedron. So the vertices of the associahedron correspond to complete triangulations, and the K faces correspond to some partial triangulations, as I've shown in the picture here. And the planar scattering form, when I pull it back onto this associahedron defined by those conditions, Sij equals minus Cij and all Xij being positive, I would get the canonical form of the associahedron. You can work out the details, but the result is just whatever I've shown here. And we see that it is indeed the right answer for the planar cubic free-level amplitude. Now, an important feature of this geometric object, the associahedron, is that it factorizes combinatorially. By that I mean, if I go to any face at Xij, where Ij is some diagonal of the n-gon, then locally the thing looks like product of a left associahedron and a right associahedron, where the left and right correspond to the polygons into which the diagonal Ij divides the original n+3 model. And since this is true, you can see that we know that the canonical forms can be pushed forward, right? And and on a product, they are just edge products of the individual things. So you can see that this directly leads to the factorization of the amplitude. Now, several other results, such as proof of CHY for phi cube theory, soft limits, etc., were shown to be particularly simple in this geometric picture.
Prashanth, just to put things in perspective, suppose I wanted to calculate a 10-particle scattering amplitude in this theory using standard methods. How complicated would that be?
No, it's not. Okay, computationally, this as of now, this doesn't help you too much, right? What it does is it organizes things in a better way. What it really does is that it tells you the set of compatible poles. So it tells you that what are all the poles that I can take to on shell simultaneously, right? That is information that you don't easily see, right? If you just write down the amplitude, like you've done here,
yes.
I wouldn't know, right? If I take some xij to 0, I don't know whether I can take xi prime j prime to 0 directly from whatever is there. But this picture sort of makes it manifest because the only guys you can take to 0 simultaneously are the ones that correspond to some facet. So it organizes things better. Computationally, this is not too efficient and so on. That is part of motivation, but for tree level amplitudes, computationally it doesn't do too much.
And can you explain to me, so suppose I did not know that this was a tree level answer. I mean, what is it that you are doing from the geometric side that is giving me just the tree level answer? Why am I not getting something? Is it the fact that you started off with a canonical form that has only simple poles as opposed to cuts?
No. So where is space time here? There's no space time here, right?
Right. Yes.
Geometric object here. So for loop level things, I won't get the amplitude. What I will more precisely get is I will get the integrand, which I would have to integrate over.
Oh, I see. Okay. And so at the level of the integrand, you wouldn't know whether there is a cut or not. I mean, it's only after you do the integral. So integrand of what? I mean, this is at the level of the Feynman parametrization or something like that.
Yeah, exactly.
I see.
Hello. Yeah, I thought it's just at the level of the propagators. I mean, because what you're writing is basically a bunch of propagators, no, in some nice form.
Yeah, for phi cube theory, it's like that.
Yeah. So therefore, if you have if you have some Feynman diagram where you have to integrate over the internal momentas, you will just get you will be able to write these kind of forms, but just as some. Yeah, it'll be the integrand, but it'll be momentous. Yeah, it'll be momentous what you have, and there is there won't be any Schwinger parameterization. It'll be just in terms.
So it's just ordinary parameter. Yeah, okay. Yeah. So it's at the level of the momentum integration.
Momentums, and then of course there will be some internal momenta you have to integrate out, and some external, which you leave it like that.
Yeah, actually it depends on what sort of variables we have. Here we had a very simple connection between these planar variables and directly the momenta, right? I mean the SIJs. For different theories, I mean the way you parameterize it can be a little bit different. So what you get may also depend on that. Okay. For simple class of things we are doing now, whatever you're saying is perfectly right.
Okay.
Okay. So this program has also been extended to various other theories. For example, tree level planar amplitudes in phi to the p theory, where the geometry is called an associahedron. In particular, for p equals 4, it's called a Stokes polytope. This has been extended to one loop amplitude for phi cube theory. We'll say more about this later. Then for theories with mixed interactions like phi cube plus phi 4.
Okay.
It has also been extended to one loop amplitudes for phi to the p theory, where the geometries are called pseudo associahedra. It has also been extended to tree level amplitudes in something called bicolor theory, which sort of is bi-adjoint theory plus certain fundamental anti-fundamental fields.
So just another point of clarification is that when you are describing these theories, what is telling us in which dimension, space-time dimension you're working in? Is there any information about that? Yeah.
No, there isn't. Actually, strictly speaking, we are in infinite dimensions because we know that there are all the Mandelstam variables satisfy some sort of Gram relations, right? Which depend on how many dimensions you are in. Right? So if I increase multiplicity, if I go to some large enough n, I know that there are going to be several relations. But we have not taken those things into account at all, right? We just assumed everything is independent.
Okay. And another question is that so the fact that you're restricting to polynomial in phi, that is for simplicity. I mean, what is preventing you from doing it for say some kind of derivative interactions? How would you is that understood or?
No, it's not. So, those things are not understood.
Okay.
Okay, so That's the end of the first part. We're going to be running short on time, so yeah. So second part of the talk is called the Stringy canonical forms. So here we basically switch gears now and talk about general polytopes. So we introduce a generalization of the notion of canonical forms. So generic polytopes with a deformation parameter called alpha prime. And these things are called stringy canonical forms. But before we define that, I need to introduce the concept of Newton polytope corresponding to some polynomial. So the Newton polytope of a polynomial P is defined as the convex hull of all the exponent vectors. So let's take an example. So suppose we look at 1 plus x squared plus y squared, right? So the exponent vectors are just 0, 0, 2, 0, and 0, 2. So the Newton polytope is the convex hull of these 3 points, which is a triangle. Now I can look at a more complicated polynomial, which is 1 plus 3x plus 5y plus 9x.
No, not able. Yeah, okay.
So yeah, I think we have lost. There's a bad internet connection going on here. In fact, I also have problems with my internet.
I also have actually. It's just a mess here. Yeah.
Yeah, I am at work and it is not good here. I guess Anindra and Justin are in their respective
No,
homes.
ACT is down. ACT is down. I'm in fact
Oh,
doing it through my
ACT is
phone.
down. Oh,
Yeah.
that's
I
a
think there's some
severe
major
open.
problem. It might be more
New
serious. Yeah.
can of worms. I'm now wondering what is happening to the kids' school.
Yeah, ACT is down. So I don't know what's happening. Yeah.
Okay, good for them.
That's why they're quiet. They've not told you.
No, they'll tell me when I go home. I am against this excessive online teaching.
Hello?
They are going nuts. The school is going nuts.
Hello?
Yeah.
Yeah,
Hi.
hi, Prashanth.
Sorry, I don't
And
know.
Prashanth, we all of us have internet problems today for some reason, not just you.
Okay.
Yeah.
Yeah, so you have to share your screen once more.
Yeah. You see?
Yes.
So I don't know where I was before it. We all had problems, but yeah, as defining the Newton polytope, I was saying that the Newton polytope depends only on the exponent vectors. It doesn't depend on the coefficients of the polynomial at all. And different complex polynomials can have the same Newton polytope, right? Because, for example, if I take the polynomial 1 plus 3x plus 5y plus 9xy plus 11x squared plus 3y squared, the Newton polytope is still a triangle, still the same triangle, because the other exponent vectors are sort of contained in the convex hull. Okay. So now we consider the following integral. Okay. So we have dxi over xi, which is a canonical form of a simplex. So the canonical form of what is called a projective simplex. They're basically defined by saying all the xi's are positive, or just the upper half, the positive octant. Right? Now we know that this, if I had just dxi over xi product over everything, then it has divergences at both 0 and infinity. So to regulate them, I can put some other factor. For example, to regulate the divergence at 0, I can just put a xi to the power xi to some positive power. And to regulate the divergence at infinity, I can put p of x, some polynomial to some negative power. Now, usually we take this polynomial to be positive because we don't want it to have any poles in the integration region. And this integral has some chance of convergence. Now the question is, where does it exactly converge? So the claim is that the integral converges if and only if the Newton polytope has to be, first of all, top dimensional, and these capital X's, which are the exponents of the coordinates, they lie in the interior of the weighted Newton polytope corresponding to the polynomial. So this is where it converges. This is the claim. And furthermore, if we take the leading order of this integral, it actually corresponds to alpha prime going to 0. And the claim is that we get the canonical function of the Newton polytope. Okay. Now there's so this integral in general has infinitely many poles, right? The simplest example we know is the beta function has infinitely many poles. All integrals in this class, it's safe to say they're expected to have infinitely many poles. But in particular, it has poles corresponding to the facets of the Newton polytope, and these poles are what we call massless poles. In fact, for any finite alpha prime, so for 0 alpha prime, we know this integral factorizes, right? Because it's just the canonical form of the Newton polytope. And we know from the properties of the canonical form that it factorizes. But for finite alpha prime, any massless pole, the integral just reduces to the integral of the. Okay, so I'm not going to prove these things, but I can give you some idea for this last claim. So the idea is basically this integral satisfies two kinds of recursion relations. The first recursion relation is basically when we differentiate this integral with respect to all the coordinates. Now, since we know that this integral is independent of coordinates, it depends only on those parameters capital X and C. If I differentiate with any coordinate x, small xi, the result has to be 0. And I get my first recursion relation, which says capital Xi times I is C times some combination of shifted integrals of the same kind. Now, the second recursion relation basically is shifting the exponent. I can shift the exponent from C to C plus 1 and multiply by the same point, right? And then I can divide the integral corresponding to each monomial in the polynomial, and that is the second relation. Now, some generic facet of the Newton polytope is going to look like x dot mu minus c, where mu is an inward normal. And we can combine these two recursion relations as follows. So I can multiply, I can dot with mu, I can dot the first relation with mu, and then I can subtract the second relation from it after I multiply with c. And I get this relation, x dot mu minus c times ip is c times some positive combination of the shifted integrals. Now, what happens when I go to the facet? That is when I take x dot mu minus c to 0 from inside the polytope. The right hand side, which is just a positive combination of shifted integrals, has to be positive. So the only way it can be positive is if my integral IP has a pole to begin with, right? Otherwise, it will be 0. So this is how we see that this integral has poles corresponding to the facets. And furthermore, you can also compute the residue. Once we know this, you can compute the residue from the same relation. And you can see that the residue, once you relabel variables a bit, does indeed correspond to the integral for the facet.
Sorry, why are you considering this integral? I missed that.
Yeah, so basically I want to define something called a stringy canonical form, which is a generalization of the canonical form. So I'm sort of working towards that.
Okay.
Right. So already we see that this integral has certain properties, right? When alpha prime goes to 0, it gives you the canonical form. And then when we go to a facet, the integral for the whole integral basically reduces to integral of the facet. These are all properties of canonical form that we defined earlier, right? So it's a candidate. It's a nice candidate, and I'm just going to define it in the next slide. Okay. Yeah, we can look at a couple of examples to see the convergence properties that I mentioned. So for example, if you just take the interval whose stringy canonical form is just a beta function, then you see that the condition tells you that this converges if the capital X is in this interval 0C, which we know is true. And the leading order result can be easily obtained from the beta function by expanding. And it is indeed the canonical form. Right? A more complicated example, if you look at the pentagon, then we get the conditions. We get the space in which it converges. You have several conditions on X and Y. And if you take the leading order, it does give you the leading canonical form of the pentagon. So having done all this, we just define the stringy canonical form to be this integral with the top form ddx. Okay. Now this can also be generalized to the case of several polynomials. So for that, we have to introduce what is called the notion of Minkowski sum. The Minkowski sum of polynomials, polytopes P and Q, is the pointwise sum of P and Q. For example, the Minkowski sum of this triangle with these two lines is a pentagon. I've just shown the process here. Right. First, I take with the green line and then the blue line. So the Minkowski sum has a sort of very nice connection with the Newton polytope. In that, if I take a couple of polynomials P and Q, and I look at the Newton polytope of PQ, then it turns out that the result is a polytope which is the Minkowski sum of the Newton polytope of P and the Newton polytope of Q. Yeah, and it can be simply seen why this holds, because to do the Minkowski sum, the brute force way of doing it would have been to take just the sum of vertices and take a convex line. Now all vertices may not appear, all sum of vertices may not appear in the resulting thing, because some of them may be contained in the convex line. But it is true that if you take linear combination of everything, you get the Minkowski sum. So if you multiply P and Q, that is effectively what you get. The exponent vectors just add up. And you're going to get a polynomial which has exponent vectors, which is the sum of all the exponent vectors of both P and Q. And the resulting convex hull is the same. By it holds. Now we can use this notion to generalize, right, to several polynomials. We just multiply the polynomials together with different exponents, and I can define a stringy canonical form for this case. Again, I assume all x's are positive and all c's are positive, and the integral converges if and only if this vector x lies inside the Minkowski sum of all these Newton polytopes of all these polynomials. And the leading order again gives you the canonical function of the polytope Minkowski. Okay, so now that we've defined stringy canonical forms, note that these have several properties that string amplitudes usually satisfy. Like for large alpha prime, these guys are exponentially suppressed. They mimic behavior such as J and planar duality. By construction, they share several properties. One property that is of interest to us is the so-called saddle point of this integral, which gives you things called scattering equations. And the claim is that these scattering equations basically provide a diffeomorphism from the interior of the simplex to the interior of the polytope. And the canonical form of P. Yeah, sure. Hello?
Yeah, do they have the hello? Do they have this infinite poles like the string amplitudes?
Yes,
I mean,
yes, they do.
And they're separated by integer values and that kind.
Yes, they do. So I'm not going to talk about it, but these guys for generic positive polynomials, right? the results are called AI hypergeometric functions. So basically, you have a bunch of gamma functions, and you have some generalization of the usual hypergeometric functions in several variables.
Okay. And they're crossing symmetric and so on. Huh? I mean, all of these.
Yeah. So those things also follow the properties of the polytope. So basically, if you want to look at something like channel duality, right? So what you do is you consider two vertices of the polytope which don't share any facet. Okay. So in the vicinity of each vertex, I know that I can easily expand in the other variables without having any holes there, right?
Okay.
So things work out nicely. I mean, saddle point.
But how are they different from the other one? I mean, it's not like the Virasoro-Shapiro amplitude or anything, right? It will be different.
That so other general properties they satisfy. They also satisfy factorization of alpha prime to 0, right? Because they're just a canonical form of that. But at finite alpha prime, generically, these guys don't factorize.
Okay.
And this is where we come to some special cases where they do factorize at finite alpha prime. And those things provide generalizations of string amplitudes.
Okay.
So that is sort of the goal. I mean, we're going to come to that.
But I thought one of the grand goals is to rule out other theories other than string theory. So this is going to help us do that. I mean,
we're not sure. So we get several candidates which satisfy all properties. Should. So some of them we don't know what they correspond to physically. Okay. So we're going to see infinitely many examples.
Okay.
Yeah.
Okay. Good.
It's open.
Thanks.
Yeah. Sure. Yeah. So the saddle point equations of these integral as alpha prime goes to infinity gives you scattering equations which provide a diffeomorphism from the simplex to the interior of the polytope P, and thus you can obtain the canonical form of P as a push forward, right, from dxi over xi product over everything, which is the canonical form of the simplex, and this gives you some sort of CHY like formula for the canonical function. In fact, for bi-adjoint cubic theory, this proves CHY. Okay. So next thing. So the Minkowski sums of polytopes have a nice property in that their shapes don't depend on these parameters Ci that we use. Of course, the size may depend, but the shape doesn't change. The Minkowski sum is a square for Ci being something positive, then it will also be a square for some other positive values of Ci. Okay. Generic convex polytopes, which are defined by inequalities of the kind we saw, do not share this property. Their shapes very much depend on the parameters used. For example, if you consider the following set of inequalities, 0 less than x less than c, 0 less than y less than c, and x plus y less than b. Now the shape can either be a pentagon or a square, depending on whether this 2c is less than d or 2c is bigger than d, right? So if 2c is less than d, then x plus y being less than d is not at all a constraint. It's automatically satisfied. So you just have 0 less than x less than c, 0 less than y less than c, which is a square. If it's not, it's an additional constraint, and you cut this square with that line, and you get a pentagon. Now, the nice thing about the ABHY associahedron that we defined is that it also shares this property. It is also independent of CIJs. Even though it's defined by inequalities, it's independent of CIJs as long as CIJs are positive. So in fact, what you can do is you can write down the ABHY associahedron as a Minkowski sum of things called AIJs with these parameters CIJ, where AIJs basically correspond to these relations that we have: xij plus xi plus 1j minus xij plus 1 minus xi plus 1j is Cij, where only Cij you set to 1 and all other C's you set to 0. Okay, so that degeneration gives you something called an AIJ, again a polytope, which is called AIJ. And if you do the Minkowski sum of all these AIJs with these parameters Cij, it gives you the ABHY associated. Okay, so it turns out that the Minkowski sum and AIJs are all just simplicities. And with Newton polytopes given by this guy, PIJ, which is 1 plus xi plus 1 all the way to product xi plus 1 to xj minus 1. And the variables are x1 to xn minus 3, and they cover the space. Now, the associated stringy canonical form for these polynomials exactly is the Cohen-Nielsen endpoint string integral. So, how do we see this? You start with the Cohen-Nielsen integral. So you have the Park-Taylor integration over m0n plus, and then you have the Cohen-Nielsen factors. Now, using SL to R invariance, I can set Z1 to 0, Z2 to 1, and Zn to infinity. And I can choose Zi to be this guy, 1 plus xi, x1 plus x1, x2, all the way to x1, xi minus 2. And you can see that for this choice of variables, the Jacobian, which should give you the Park-Taylor, just gives you dxi over xi product over all I. And the Cohen-Nielsen can be split into two guys, right? So initially the Cohen-Nielsen is over all I less than j. I can look at I being j plus 1, j being I plus 1, and j being I plus 2, and j being greater than I plus 2. So for things where j is bigger than I plus 2, we know that Sij is minus Cij. So that's how we define the ABHY associahedron. So those guys just give you Pij power minus alpha prime Cij. For the other guys, you can see that they combine nicely to give you xi to the power alpha prime xin. And this is precisely the stringy canonical form of these polynomials. So the stringy canonical form corresponding to ABHY associahedron is actually the Cohen-Nielsen string. Okay. So a remarkable property of this integral In is more special than other stringy canonical forms is that it factorizes more nicely than the other guys do. It factorizes into products of integrals of the same kind.
Is there some, hello? Is there something for the open string amplitude? I mean, this is the closed one, right? I mean,
this is open one, right?
Oh, this is the open one. Okay, sorry.
You'll have to take 2 copies of this guy and yeah, there are things. Yeah,
there are things.
There are analogs. Yeah, they have some convergence issues and so on, for which you need to shift the exponents by some integer values. Yeah, but there are analogs. Yeah. So, sorry, how much time do I have left? I seem to have.
What is a natural cutoff you think, Prashanth, to end naturally?
And naturally, I can at least tell you why this guy factorizes, right?
Yes. No, I think you should tell us the big picture, and especially where you think this is going.
Yeah. That would be good. Yeah. That would be
good. So yeah, let me tell you the big picture then. So this guy has a nice property that it factorizes into 2 integrals of the same kind, right? So to make this manifest, you go to some nice set of variables which are called U variables. Okay, let's just skip over the details. Okay. Let me just yeah. Yeah, so basically these variables can be translated into a nice set of variables called U variables, which where you basically go from the inequality sort of description that we have to a vertex description. Right, the polytope can be defined in 2 ways, either by convex hull of all its vertices, or it can be defined as a set of inequalities. So the dual picture where you go from being defined by inequalities to being defined as a convex hull. And the nice thing about these new variables, which are called these U variables, is that the convergence conditions are really simple. So we had some complicated convergence conditions, right? x had to lie inside the Newton polytope, which was defined by something, and so on. But in these new variables, all that you need is the exponents of uij's be positive. That's all. That gives you convergence. And this is basically a rewriting of the integral in new variables, right? By introducing these new variables. And these new variables satisfy some very special relation, which is called the U equation. Okay, which is shown in this red color here, right? So uij plus product over kl crossing ij, where ukl is 1. So what this relation tells you remarkably is that if I take some uij to 0, okay, uij being 0 is some facet. Okay, if I take some uij to 0, then all ukl, where ukl are incompatible. That is, they are facets which don't intersect ij. Those go to 1. So these equations, in essence, provide you a binary sort of presentation of the associahedron. So there's a 0-1 sort of presentation of an associahedron. Facets correspond to 0. If you go to that facet, all the incompatible things go to 1 and drop out. Okay. So these guys are called configuration spaces which satisfy such equations are called binary geometries. You can see that the Koba-Nielsen immediately splits, right, because of this property. Whenever I go to uij going to 0, the Koba-Nielsen immediately splits into a left and a right. You'll see that even the Park-Taylor does the same. The Park-Taylor also splits exactly due to this property. And that will tell you that the integral In factorizes at finite alpha prime. Okay. Yeah. So big picture is that this happened for AN. Then there is a generalization of this thing which are related to all the cluster types.
But in this open string amplitude, I mean, I guess you have the tachyon amplitude, not the photon amplitude, right? I mean,
just the tachyon amplitude, yeah.
The photon one you don't have. I mean, del x c to the
Photon
ik.
one we don't have, yeah. Right. Yeah.
In fact, as a follow-up question, would you be able to get things which correspond to fermion scattering? Or, yeah.
As we don't, right? Because we don't even have in the alpha prime point, the field theory limit, we don't have the positive geometries, right? So presumably no. I would think those things have to be developed before we can.
Right.
Yeah. But just as a naive question, I mean, like what does one gain by doing all this? I mean, I'm sorry to ask, but like, okay, we have these amplitudes, and I mean, I thought one of the goals was to sort of somehow classify all the possible, interactions or allowed and consistent with certain like unitarity and so on, and just restrict yourself to.
You candidates, right? These guys definitely give you candidates which satisfy everything.
Okay.
Whether they correspond to something physical or not has to be checked.
Okay.
These guys give you allowed things, right?
But isn't it more than that? I mean, I thought, I mean, locality is emergent here. It is not inbuilt. I mean, usually in QFT, yeah, usually in QFT we have locality inbuilt and then we make some statement.
Not just locality. Yeah. Everything emerges from the geometric picture. Nothing is put in by right? Yeah, okay. As of now, there are some theories which we know, and it seems like this is not very radical and stuff like that. But the hope is that by applying the same set of ideas elsewhere, we can indeed get something new.
Okay.
But you got this impressive derivation of the CHY amplitude. Isn't that something that is telling you that there is something? Yeah.
Not just that, right? Even other properties like.
Yeah, no, I'm saying that as an example. I mean, it's not. This is not completely.
Right.
Without merit, yeah.
And there's no reference to anything, right? We haven't talked about spacetime. We haven't talked about world sheet. Done anything, any of that, right?
Yeah.
Okay. So the claim is that let me finish because I think I'm way over time. So these guys, the open string integrals we talked about, right, and the associahedra, they turn out to be special subclass of a class of things associated to cluster algebra, and you can generalize whatever you had to finite type cluster algebras. Okay, I'm not going to go into the details, but the point is that all of them, they are also binary. They satisfy all properties that open string integral did. They satisfy U equations which are slightly more general, where instead of just being products of U's, you have some powers. Okay. And in fact, you have such guys associated to all the cluster algebras, which are labeled by Dynkin diagrams. And the classical ones, let's say classical ones, ABCD, they are in fact associated to some, they have information about one loop, 5 loop amplitudes. Okay, so AN is just what you know, whatever you talked about. B and C are called cyclohedra, which correspond to tadpoles in 5 cube theory. And DN basically contains all the information about one loop. And there are stringy analogs of all these guys. Okay. So now I come to my work. So basically, a natural question is whether the only binary geometries are these generalized associahedra or products. Right? The natural question to ask. So we answer this question in sort of negative by providing infinitely many new examples, which fall into broadly two classes. One of them is called generalized Permutahedra, which is sort of very large class of polytopes which contain type A and B subclasses. And there are also other binary geometries which you can get from degenerations. By degenerations, I mean you from the stringy integral you can omit certain polynomials. If you omit certain polynomials at random, you run into trouble. But in a controlled manner, you can delete some of those polynomials, and you could still get integrals which have this kind of computation. Yeah, that is the big picture. I mean, with lack of time, sorry, I went over time. I don't think some details.
Right. Yeah. Thanks. Just for the 5-4 theory, there you said somehow there's some weighted sum of the polytopes, or
yeah.
But that weight is it?
Weight is completely by factorization of the amplitude.
It's fixed. It's fixed. There is no ambiguity.
There's no ambiguity. It's fixed by factorization properties of the amplitude. So we give an independent prescription to compute the weights. Okay. So without saying anything about factorization, you can compute the weights.
Okay.
But you can show from first principles that the weights are of course constrained by factorization, and those constraints are enough to determine them uniquely.
Okay. Last time I heard Alok's talk, somehow there was some ambiguity in the weights. Maybe maybe it has changed.
Yeah, that was it.
Yeah.
Yeah. It follows from factorization. There's nothing new there.
Okay.
Yeah.
Okay. So you were collaborating with Songhae online during
yes,
the right, I see.
Yes. I was supposed to join, but
yeah, I know the situation. Yes.
Yeah.
Okay. Any other questions?
Yeah.
So Prashanth, can you just maybe briefly in a minute or so tell me? You said crossing symmetry is sort of inbuilt into the geometric picture. How does one see that?
Yeah. So basically, what I meant by that was for certain general polytopes. So they need to have this property that you can find two vertices which don't have any common facets.
I see.
Okay. So for very simple things like simplex, that fails, because in a simplex everything is adjacent to everything else, right? So that sort of thing fails. The whole point is that we know that by definition we know that the canonical form on any vertex goes to 1, right? So what that tells you is that if I expand my integral, by taking sufficiently in many x's to 0 to go to that vertex, right? Then the integral goes to. So in some neighborhood of that guy, right? These guys will have some polynomial growth. Will have some simple looking polynomial growth, right? Continue. So if I take two guys which are far apart, they don't have any facets in common, then you are sufficiently far away from the poles of the other guy, and I can expand my amplitude in the other variables there. There are no poles, right? So I can do an S-channel expansion where there are no T-channel poles, and I can do a whatever T-channel guy with.
Okay, I see. I see. Okay.